So we got. So we have a card that's being drawn from a standard 52 card deck. Okay, we want to know the probability of getting a 7 or a king. So we go to our handy dandy deck of cards here, and we look to see how many 7s or kings there are in the deck. All right. So I got my 7s here, and I got my kings here. Right. So this is, I mean, it might be the exact same problem that we did last class, or it might just be a slight variation of it, but it's never a bad idea to just review the topic. But yeah, it is a matter of just saying, okay, well, how many cards, if I win a game based on selecting either a 7 or a king, how many ways are there in which I could win the game? There are 8 ways I could win the game, and there are 52 cards overall. But again, the formulaic approach, that's super tiny. The formulaic approach would have it so that we would look to see the probability of getting a 7 plus the probability of getting the king. All right. Now, we have to make a determination of whether we're dealing with mutually exclusive events here. Right? These are not mutually exclusive. I'm sorry, they are mutually exclusive. Mutually exclusive. Right? The mutually exclusive means that there is no overlap. Right? So ME for mutually exclusive. Another word for it is disjoint, but mutually exclusive, I think, tells the tale a little bit better. You know, so there are 2 sets that are mutually excluding each other. So one of them saying, you get out of here, and the other one saying, no, you get out of here, and they're shoving each other away. Right? So mutually exclusive means no overlap. So there's no way that you could have a card that is both a 7 and a king at the same time. Right? So that's your license to just simply add the probabilities for each one. 4 out of 52 plus 4 out of 52. So the formulaic approach would also give us 8 out of 52. So the benefit of the formulaic approach, as opposed to the, just counting up cards, we talked about this before, it really just boils down to the idea that sometimes you don't have cards to count. And even if you did have cards to count, maybe there's so many of them that it's just not practical to count them physically. All right. Now, the next question is talking about prime numbers. 2 numbers are prime of 2 numbers. Geez. A number is prime if it's a number bigger than 1. So any number has got to be bigger than 1 that is divisible only by 1 in itself. Now, we talked about this when we were going over sample spaces, but in an effort to not flip back and forth pages, I thought it was just a good idea to put definition here and just go through a deck of cards, all the possible numbers that would be in the deck of cards. So 2, 3, 4, 5, 6, 7, 8, 9, and 10, and just identify which ones are prime. All right. So they're all bigger than 1. So the part of the definition related to a number being greater than 1 is satisfied. So that's good. Only divisible by the number of 1 in itself. All right. So that would be 2, 3, 5, and 7, and that's it. All right. Because in addition to the number 4 being divisible by 1 and 4, it's also divisible by 2. 6 is divisible by 1 and 6, sure, but also 2 and 3. 8 divisible by 1 and 8, but also 2 and 4. 9, 1 and 9, but also 3. 10, 1 and 10, but also 2 and 5. Right? So there's an also for every number that I didn't highlight. Right? So what we're focusing on here are just the numbers 2, 3, 5, and 7. So the key ingredient there is the number 7. Right? So I have my two sets here. The set of the number 7 and the set of primes. There is an overlap, right? Because when I look at my prime numbers, 7 is part of that set. So I'm going to go back to my diagram. I'm going to mark up based off of the prime numbers. I'll do that in green. All right, so all the 2s, 3s, 5s, and 7s. Right. So you see that I got the 7s double highlighted. I mean, you might be able to barely see it, but it's there. Right. I have it highlighted in yellow and also in green. So when I'm counting up the number of values that satisfy these conditions, I see that there's a total of 16 out of 52. So that would be my answer, which is good, again, if you have a deck of cards to work off of. But if you're doing it with a formulaic approach, what you'd have to do is find the probability of getting a 7 plus the probability of getting a prime. All right. Now, this is where it gets a little dicey, because if it's going to be a prime number, we want to make sure that we're only including the prime numbers that haven't already been counted. All right. So a prime number and not 7. So I only want the prime numbers that are not 7. So 4 out of 52 for the 7s plus all the other ones. So the probability of a 2 or a 3 or a 5. So it's a little bit more painstaking in terms of the work, but we'd be looking at 4 out of 52 for the 2s. I'll highlight. So it's an or within an or, the way I have it set up. Plus 4 out of 52 for the 3s, plus 4 out of 52 for the 5s. Let's make this one a little lighter. Too light. Let's go with a nice little pink there. There we go. And from there, we can get our 16 out of 52. So that's another way of handling it. So we could have done it the formula way. I'm sorry, the counting it up, the sample space approach, the one formula approach. But also we could say, all right, well, what if I take the probability of getting a 7, add to it the probability of getting a prime number in general, and then subtract off the overlap? Right. So I could look at this and say, all right, well, I'll subtract off any number that is prime and 7. So I'd be looking at the complement here, right? Prime and not 7 versus prime and 7. So everything else. Right? So 4 out of 52. The prime numbers, there's a total of 16 of them in the set. All right, so 16 cards. Now, you see that I only highlighted 4 cards, but you got to remember there's 4 cards and 4 suits. So each one of these cards is going to happen for the hearts, the diamonds, the spades, and the clubs. So that's where I'm getting my 16 from when I'm looking at the primes. Now, I can account for all of those, but then I have to say, oh, wait a minute, the prime and the 7, well, that's all the 7s. I already double counted them. So I'd knock off 4 out of 52. This is, for this particular question, the best approach is probably just a little bit of reasoning, right? Really just kind of thinking about it, because if you go right back to what I just wrote, the 16 cards that are prime, that was our answer. Like all of this other work wasn't really necessary, but I got to kind of train you for all these other approaches, because just because this problem worked one way doesn't mean other problems are going to work the same way. Right? But once you realize that 7 is included in the set of prime numbers, then it's like, oh, well, I don't even have to worry about the 7s anymore because I've already got them covered. Right? So it's kind of along the lines of, a set of black cards, and including the like, for example, clubs or spades. Those are also black cards. If I say the probability of getting a black card or a club, like, well, the clubs are already included in the black card, so forget about that. I'm not even going to bother with that, right? So it's kind of, you're looking for the trick through the maze. You're looking for the little shortcut that saves you time and energy, because if you could find that, then you're going to be in good shape, right? But you always have that formulaic approach to fall back on. It's just a question of whether or not that's the most efficient way of doing it, right? So same idea, prime or even, or at least similar idea. We know the prime numbers again, 2, 3, 5, and 7. I don't know what I was trying to write there. I eventually settled on the number 5, but that took off on me. It's a total of 16 cards. Because again, the 2 occurs 4 times, the 3 occurs 4 times. Right? So I'll just make a little note here, 4 times each. Try to make it look somewhat reasonable. All right. So when I look at this one in a vacuum, I would say probability of getting a prime number plus the probability of getting an even number. And then I would start, that's where the thinking part of the process starts. Like, is there a way that I can have a prime number that's even at the same time? Well, yeah. Right. So we'd be looking at, and let me just kind of box this in so it's clear what I'm talking about. The primes are here. The even numbers, let's just kind of pull that off also. The even numbers, 2, 4, 6, 8, and 10. Also 4 times each. But we do have some overlap, right? The overlap happens with the number 2. Number 2 is in both sets. So what I can do is I can eliminate it from one of the sets, right? So I would adjust this to say an even number and a number that is not 2. Right? Because I've already, when I count my prime numbers here, I get 16 out of 52. I've accounted for all of my prime numbers. One of those prime numbers is the even number 2. So I'm going to eliminate this from the set. 4 times each on these 4 values is going to give me another 16 cards. These are 16 new cards, right? Ones that I haven't accounted for yet. So 16 out of 52, add them together, and I get 32 out of 52. All right. I just kind of settled on that approach for this type of problem because, you go back to the other techniques, you see like part B, we got all these other techniques that we could use. We got a total of 3, but there's even more out there. You start kind of getting into a rut where it's like, do I use this technique or that technique or that technique? Like you just kind of settle on your favorite technique and then resort to the other ones if they're needed. You know, I kind of look at it like if I have a display, if I have the diagram in front of me, I'm going for that every single time, right? But if I don't, then I'm probably going for a technique like this one, and then I settle for that last one, right? So the solution that I put for part B, that's actually the order of my personal preference. That's the way I would prefer to do it. I'd like to do it by the diagram first, then use this idea of, okay, when I account for my first set of values, did I account for the overlap in doing that? And if so, then I'll eliminate that from my second set, right? And then if all else fails, then I go for the third technique, which kind of requires you to do elements of the first and second technique anyway. So it's sort of like overkill, right? D is kind of like my favorite type of question. Not to say it's my favorite question, but it's a good question to get you thinking about how probability could be simplified in a way that it just makes it more streamlined so that you can arrive at answers in ways that maybe you didn't think were possible. And it could take a problem that might take you 10 minutes if you do it right, and make it so that you can get it in your head after like 10 seconds, right? So what I would do is I'd look at this and say, okay, what does it mean, right? And so it's not like, that's not the entire sentence. It's what does it mean, ... right? So what does it mean All right, now the ... would be, in this case, followed by, for a card to be not read. Because we have a pretty solid idea of what it means for a card to be a 7, right? And that's just kind of tongue in cheek here. You better have more than a solid idea. It's saying that it's 7. That's the number on it, right? But when a card is going to be not read, that means that it's got to be since it's a binary situation, there's only one other possibility for color. It's got to be a black card, right? Must be a black card. All right. So that's my answer here for that rhetorical question that I really just asked myself. What does it mean for it to be a red card, not a red card? It means it's a black card. So now I take that idea and I say, okay, well, doesn't that mean that instead of asking the question probability of 7 or not red, wouldn't I be really asking what's the probability of a card being 7 or black? Right. Now, if you reflect back, you see that that's a problem that we've tackled already. But even if it wasn't, you're now kind of, you're cutting out a lot of the fluff where you're like, okay, some of this stuff is here as a distraction. It's kind of like if I were to say, what's the probability of getting a card that is not an even number? And you say, okay, well, you're talking about an odd number, right? If I say that it's not a negative number, okay, so it's 0 or larger, right? Or if I say it's not negative and it's not odd, then you can start thinking about what, instead of what it's not, start thinking about what it is, all right? It does tend to help. So then I would look at this and say, okay, probability of 7 or probability of black. But is it really just black? You got to think about overlap. This is another case where it's not mutually exclusive, meaning there is some overlap. You can have a card that is 7 and not red at the same time, a card that's 7 and black at the same time. So I want to make sure that I'm taking my probability of 7, that's the easy part, 4 out of 52, and then adding to that the probability, since I've already gotten the 7s accounted for, probability of getting a black card and a card that's not a 7. So here, in the setup of the problem, I had not red, so I transformed that into black, because saying a card is a black card is a simpler statement than saying that it's not red. But here, saying that a card is not a 7 is a simpler statement than the alternative, because the alternative would be, okay, well, if it's not a 7, then it's a 2, a 3, a 4, a 5, a 6, an 8, a 9, a 10, a jack, queen, king, or ace. Right? I don't want to write all that stuff. I'll just focus on the fact that it's not a 7. Right? So when you go through all of the cards in the deck, just focusing on the black ones, maybe you just go with the spades, for example. There's 13 spades. Well, I'm not going to include the 7, so now I'm down to 12. All right, so I got 12 spades. And I also have 12 clubs. So that gets me up to a total of 24 cards. So 24 out of 52, result 28 out of 52. All right, so it takes a little bit of thinking, but I would suggest that a little bit of thinking in the early going when it comes to probability saves you a lot of time and energy down the line, because it's sort of along the lines of packing for a vacation. I always joke around with my wife. She doesn't find it funny, but I always joke around with her that when she's packing and stressing over the whole packing experience, especially if we're going somewhere local, like, well, we're not going to the middle of the wilderness. They're going to have a Target there. So if we forget toothpaste, we'll just buy it when we get there. Right? So that's fine. When you're solving a probability question, you forget like one little tiny detail, you can correct for it in the process. But okay, so you forgot the toothpaste, you forgot the toothbrush, you forgot, socks, you forgot, it starts adding up. That's okay too. Like, I mean, it's not ideal, but at some point you're probably going to have to buy new socks. You're probably going to have to buy a toothbrush and toothpaste. So it's like, okay, I can live with that. Right. But then you forget your medicine, your prescription medicine. And you're like, oh, that was a big one. Right. That was a detail that kind of derails everything. Now, instead of making a quick trip to Target, now I got to call the doctor. I got to get a prescription sent down to wherever I am. And if I'm in a foreign country, how does that work? Like it's a nightmare, So that's what happens with probability, where if you miss a variable early on in the process, yeah, it could be that you forgot some socks. It could be that you forgot the toothpaste, but it could also be that you forgot your medicine, right? If you forgot your medicine, then that's a crumble up that piece of paper and chuck it, because everything that you just wrote down is worthless, right? It's almost never going to be a case where you can just change a minus to a plus and you'll have the right answer. It's usually right back to scratch, right? So taking a second or two to think it through in the early going, it makes a big difference. Right? So let me stop that